I like the way you say that. I think I have a question. Like, you would be the best one to know. All right, let's see. Bum. That'll work. We'll get you out of the way. I'm sorry, do it again. Number 12, 6-1?
5.3.
5.3? Okay. Oh, okay. This is a good little quick review. If I gave you this function, I'm going to build my way up to there, right? Let's do what would this be? Because effectively, the derivative kills the integral because the integral is antiderivative. So of course they kill each other, right? They kill each other in a weirder way than we're used to, right? That basically goes in. So now let's look at your specific one. There might be some weird stuff going on. For example, I can't see where this should. Oh, there's the y. So yours on number 12 says r of y. So it doesn't matter. 2. All right. What's the first thing you notice? Is this in the right form to apply the rule? What's the difference I have to take care of? Why is that not in the right form? Yeah. I really want you to understand. So if I said, back in the day, and I'm like, take the derivative of this. If I take the derivative of that and I get this, is that correct? No. Shit, no. Why? Because is that in the form that I can then apply the appropriate rule? No. Of course, how do I make this in the right form? X to the -6, and then I can apply the rule. So this idea of it has to be in the right form to apply a rule. That's the general idea for derivatives and neural. So I have to be in this form, constant up to variable. So how do I switch that? What happens if I do this?
You put a negative in front.
Yeah. And that makes sense because the integral is built on that, the width being 1 over, b minus a over n. So if you switch the a and the b, doesn't that become the opposite sign? That's all that is. And then you can apply this rule directly. So now you can do r prime, because that's all it's asking you to do is find the derivative, thank God. Because could we integrate this? Not currently. After the first section in chapter 2, you would be able to integrate this. But, too bad for us, we're not doing that, so. But thank God, it doesn't even want us to integrate it. So don't even, I don't know, sometimes people look at a problem and think it wants you to integrate. No, it wants you to differentiate. I like it. Is that all right? No? So now it's going to work exactly like this would do. Because it's exactly in the right form. So if I take this guy's derivative, these effectively kill each other, but in a specified way. And why does chain rule not happen here? Why does chain rule not show up? What's the inside variable? Here, and here, chain rule didn't happen, did it? Why? Because the inside variable was just x. It wasn't x squared. It wasn't sine x. It wasn't natural log of x. Right? That would be a chain rule.
Then you would have to do
The chain rule.
sine x squared.
Yeah. As always. So all right. What's the inside function here? What's the inside function here? What's the inside function here? Sine x. So if I want to do this guy's derivative, it would be, the rule says that goes here, And then chain rule says, oh, you're doing the derivative. All right, are you done with the form? Great, now do the inside function, right? So it'd be times cosine x. All right, so effectively, that's really nice. It doesn't do shit to the function itself. You just gotta be careful about putting the stuff in, when is it chain rule. But effectively, this doesn't change, because this and this kill each other. Because what's another name for the integral? Antiderivative. So of course derivative and antiderivative kill each other. Alright, I like it. Is that cool? Anything else? Yes?
21 on 6.1.
Alright, sketch the region. On here, okay. The tangent x and the 2 sine x, is that right? 6-1?
Yeah.
21, 6-1?
Yeah.
Tangent x, 2 sine x? Okay. That's all it says, right? Oh, it gives you this. Right. So what's important here is, so if my area ends up looking like, all right, good job. So here's negative pi over 3 to pi over 3, and if I have a top function and a bottom function, then that's easy. I just integrate from negative pi over 3, pi over 3, top minus bottom. Yes? What do I have to be careful about though? What could happen?
Well, one comes on top of the other one.
They could cross over, in which case the top and the bottom switch, right? So how do I find out if that's going to happen?
Sketch it.
Well, how do I sketch it? How do I find out if they're going to meet? They can meet to each other. They can equal to each other. Then you're back in everybody's favorite part of pre-calculus, which is solving trig equations. Right? So now you gotta solve that. How do you solve that? I'll give you a
break
clue.
up 10x.
Yes, break it up into what?
Sine over cosine.
Sine x with cosine x. Do not kill the sine x's, because then you're losing a possible answer. Right? I would multiply the cosine up, I would subtract this over, then I would factor it, set each factor equal to 0, same old shit. It's kind of funny how even though it's trig functions, yeah, my over factor, set it equal to 0, that process is like, I don't care what the shit's in there, just do it. Yeah? Just do it. Does that give you enough to?
Yeah.
'Cause
Well,
if
I
it does-
got that far, I guess the other thing I'm confused about is.
Did you find out where they
So
meet?
yeah, when they meet at like basically the bounds and then also zeros what I got.
Ah, good,
Yeah.
okay. So they do meet at the bound, so it sort of looks like, it doesn't look like this at all, but it has this idea, right? It does this, maybe something like that, and they're the equal here.
Yeah, exactly.
Yeah,
Almost
something like, oh screw it, my scale sucks. But so somebody's on the top from here to 0, and then it's on the bottom from 0 to this.
Yeah, so.
So you have to
could I
make,
separate the integrals?
Separate integrals.
And then add them together with something?
yeah. Because the idea is, it's the integral from negative pi over 3 to pi over 3 of stuff. Dx. But the stuff has something weird happen at 0. So then this equals negative pi over 3 to pi over 3. This part of the stuff. Yeah, out of pi over 0. Plus 0 to pi over 3 other stuff. Right? Basically, top minus bottom, and then they switch. Yeah. Does that make sense? I know that's very kind of abstract level, but yeah, that's why you want to find if they meet somewhere in the middle, because then you have to break up your integral, because the integral has to be top minus bottom, and if they switch somewhere, just make two integrals. If I find this area and add it to this area, isn't that the total area? That's all it's doing. Yeah. Each integral is an area. It asks 10. I made it to 10. All right. Part of me hates that I celebrate that, but it's all right. Anybody else need this sheet here? Yes? Yes? Everybody else has that sheet? Oh, shit. All right. Well, damn it. Let's see what I can do. Started working on the other side. Who else? Does anybody else need that? Everybody's got it? Oh. Okay. So we need to finish up number 2 on the other side. Some of my room, but too bad for me. So number 2, can you please, we did the other 2 last time. Can we finish this one up? Sort of. You got to the point where I was bored, and then you just throw this thing old calculator, who cares? Right? Simple. This is the one place, remember what's the point here? You're so used to seeing 0 and just ignoring it. Well, what happens when you plug a 0 in, you don't get 0. Oh shit. Be really careful. Don't just ignore 0 if it's one of the limits, because the functions inside might not become 0. Right? Only if it's polynomial. Okay. Number 1. So look at number 2 real quick. Just do a rough sketch of these. We didn't do this, right? I don't think we did. Okay. Before you do a rough sketch, what do you have to figure out? No, that comes later. We draw the region first, but before I can draw the region, I want to know where they meet. Because do I give you any x from x equal to blah? No, so it's going to be between where they meet. Recommend once you solve for the value of the variable it's a function of, right? The values here are plus or minus 2, immediately make them points, and then you can graph. And then all you have to worry about is what the shit's going on in the middle. And really all you got to worry about is who's on top, who's on the bottom, right? Okay. So is it pretty cool that worked there? Did he do that already? So what's the point, the first point, 2 comma what? 7. You can real quick check. Don't you get 7 in both? They have to agree because that's where they're supposed to meet. And then of course, negative 2 will also be 7 because the x is being squared, yeah? Okay, let me stop for a minute. This kind of makes sense because what shape do both of them take on?
parabola. One of them's down, one's up. So of course it's going to be symmetric where they intersect. All right, let me stop for a minute. So here's what I normally do when I have just parabolas, right? And actually I do this whatever the function is. I know they're going to meet at 2, 7, negative 2, 7. What's this guy at 0? 0, 3, right? What's this guy at 0? 11. Okay, so 0, 3. So I could have made this better. It's too bad for me. I didn't. Too bad, Jeff. I don't care. Now watch. This is a sketch, yes? Is that scale good? No. Is that scale good for a sketch? That scale is beautiful for a sketch. It's beautiful. That's a perfect scale for a sketch. Now I just need 2 other points, a 2, 7, 2, negative 7, right? Negative 2, 7, sorry, turn those around. So 2, 7, negative 2, 7. So then one of them is an up parabola, and the other one is a down parabola. There you go. Look at that. If the point of this problem was to sketch that, is to graph that, I would give you like barely any points. It's bullshit. But is that the point of the problem? No, I just need that to work from. So it could look like that. Look at that. That's disgusting. Right? I could say that about my own work. That work is gross, Jeff. But is it good enough? Oh, hell, it's beautiful for this. Let me stop for a minute. Anything I just did weird? It's kind of beautiful when they don't give you, when they don't give you this. Because if you find where they meet, you plot those, and you just need one more point in the middle for both, and you can see who's the top, who's on the bottom. This is all you really need to know. Okay, now we talk about what method we're going to use. I'm rotating about what? And what does that look like? Yeah, so negative 2. That's what I'm rotating around. Yes? Okay, so if I wanted to use disks, it would have to be integral d what? Dx. Is that cool? How did she know it was dx?
Y equals 2 horizontal.
Say again?
Because the axis of rotation is horizontal, right?
Yes, because it's parallel to the x. I love it. It's parallel to the x. It's horizontal. I love it. And disks is direct. If you're going something around this, that's like the x-axis, dx. If you're going like this, like the y-axis, dy, right? And then shells, other way around. So does it look like disks will work here? Yeah, our functions are functions of x. And they're easy functions to integrate. If one of them was natural log of x, what would we do then? Shells, because then I could solve it for x, get e to the y. Now that's easy to integrate, right? All right, so I really want you guys with me. What kind of tells you disks or shells? One could be, what are they functions of already? Right? Another layer could be, all right, if they're functions of x, are they functions I can integrate? Because if not, then I can't do it that way, right? Natural log is the perfect example, because we cannot integrate natural log of x to save our lives, but we can integrate e to the y. That's kick-ass. Yes? I really want you guys with. Okay. Start crying, please. Okay. Trust, I know this shit is weird. I know it is. Key in on the triggers of the problem that tells you what to do. And part of the problem could be picking wrong, going down a little bit and going, well, I can't do that. Well then, okay, go back up, start over, do the other method, right? Not a big deal, it's part of the process. Okay. So now that we have identified, we're using what now? Disks, because it allows it to be integral dx. So we're using disks. Integral blah 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 dx. Right. So if I want, I can pick anywhere in here, because I'm gonna go through this whole region, so I can pick anywhere I want to in there. And I'm gonna identify the radius then. Right, because that's really what the disc needs, is just the radius. Which is one reason why people like disc better, it just needs radius, but cylinders are actually, I think they're better. What do I need to figure out then? Does my region hug the axis of rotation? No. So you just pick a spot. You don't have to pick the same spot, any spot in there. For this one, if I start at the axis of rotation, what do I hit first?
X squared plus 3.
So let me draw my radius in. So here's my radius at this point. Bang, there's that. That's going to be the which radius? The which, as in WHIC. The inner radius. Hold on. Because can anybody see in your mind's eye, if I rotate this, isn't it going to have this weird empty spot in the middle? Because the actual thing is here, and if I rotate that, it's going to leave all this empty spot in the middle. It's going to be this weird, like, I don't know. It's really weird. It's like a tire rim or something? I don't know. So what's the inner radius? How long is this thing I just drew? What's this wall? What's this wall? It's the up parabola. So which one is it?
X squared plus 3.
X squared plus 3. Now please, dear God, what I'm about to say happens all the time. I just drew that line. Right? Which wall is bigger? The x squared plus 3, right? Minus the smaller value, right? So this is y equals x squared plus 3. That's the bigger value. Minus, what is this again? Y equals -2. So x squared plus 3 minus -2. That's the inner radius. Otherwise known as x squared plus 5. I think. Keep going. X squared plus 3. Yeah, okay. And real quick, let's check it. At 0. At 0. Can you just tell me how long this is? Just tell it to me. Just -2 to 3. How long is that?
5.
I'm going to put a 0 in here, I get. Okay, so that looks pretty good. It does do what it's supposed to do, it seems. What's the outer radius going to be? So now, just so I can kind of see what the hell I'm doing, I go somewhere else. I go past the first wall and I go hit the second wall. So what's this outer radius going to be?
11 minus x squared, or
Do it again.
it's going to be 11 minus x squared.
11 minus x squared is the top, minus the bottom, -2, so plus 2. So our outer is 13 minus x squared.
That looks like 13 times x squared.
Say again?
That looks like 13 times x squared.
All right, so this is all about giving yourself a graph. How could I have made my graph a little better? Did I really need, I could have started, I could have kind of zoomed in a bit, right? Give myself some more room, but this is fine. I really want you guys to understand what it is you have to focus on step by step. First thing, find out where they meet, if necessary. Second thing, sketch the region. Third thing, discs or shells. And of course, once you know discs or shells, discs needs, in this case, inner and outer radius. How do I know it needs an inner and outer radius? Because the region is not hugging the axis. Okay. All right. So now it's just, so in general, it's going to be pi r outer squared minus r inner squared. So now it's going to be the integral from what to what?
-2 to 2.
Yeah, that's what x is doing, right? dx tells you what is x doing? -2 to 2. r outer squared will be 13 minus x squared minus our inner squared. Does anyone notice one little thing you could do that would make this a little better? Is this region symmetric somewhere?
Symmetric across the y-axis.
So you could do twice this from 0 to 2. Yes? If you don't notice it, who cares? Right? No big deal. And then that is where I'm going to stop, because you should be able to FOIL and then integrate. It's just a polynomial and then plug shit in. Is anybody upset that I'm stopping there? I mean, this needs to be the once you get here, like, okay, think on maybe? No? So real quick, what if I were to have that same region by the way, on a test, you can't just say, you know, I'm bored like you are, Jeff, so I'm not going to do, no. You do it. Okay. What if I had that same exact region? So let me copy that region. Yeah. Oh, there you go, Jeff. All right. Punch it back. But I want to rotate around x equals 2. Let me just remind us, this one was, what was that, 11 minus x squared, sorry? Yes. So I gave you, everything's the same except instead of saying y equals -2, and now I say x equals 2. That's my rotation axis. Why did I put that there? Yeah. Sorry. I copied too much. So instead of saying y equals -2, I say rotate around x equals 2. So what's the very first thing we encounter? What would disks need for this?
Function of y.
Yeah, it'd be integral dy, because this is something like the y-axis, right? Now, technically, I could solve those for x. You can't, we're not going to, right? That's gross. You add some radicals, do you really want that? It would actually work, but it would be much worse than it needs to be. Therefore, I think I heard somebody say, obviously, if this doesn't work, then we're going to use, holy shit. Shells needs this stuff, right? RH. Yeah. So disks needs dy, shells needs dx. And again, I'll go over this in a minute. Kind of review real quick why those are the way they are. Let's just keep going here. So now I'm going to rotate it like this. Okay. So what do I locate in my picture? When I'm doing disks, I need to locate my radii. Yes? Or radius if I just need one. When I'm doing shells, I need to locate a rectangle. And I kind of gave it away just there, but is it going to be standing up or laying down?
Lay down.
No. So your rectangles will always be parallel to the axis you're rotating, because I want it to be this kind of thing, right? So since I'm rotating around this, I can put it anywhere I want to, just anywhere you want to. Just put a rectangle. Not like over here. It's going to be in the region. Stop. Where could I have put my rectangle otherwise? Couldn't I put it back here? Yeah, Jeff. What's locating my rectangles? Is some y value locating my rectangles, or is some x value locating my rectangles? You can see what I'm saying? Like, how would I locate this one versus this one? Didn't I move a little bit further that way? So it's x. That's locating. I really want, that's why this is dx.
Because to find my rectangle, I have to move along the x-axis. Maybe, and here, to find the disk that I want, I move along the x-axis. Every time I move along the x-axis, I got another disk. Move along the x-axis, get another disk. Okay. Sketch the region, throw in your axis. If it's shells, draw in a rectangle. Right? Where's my radius? How do I don't care which method you're doing. How do you find the radius? You start at the, how do we find the radius? You start at the center. Just like if you have a circle, you start at the center and draw out, right? So if I start, in the center, of course, is the axis, and if I go to my rectangle, how long is that?
2 minus
2 big minus x small. It's always big minus small. It's insane. So if you guys just draw in some shit, you have a visual cue of what's going on, right? So how long is this? Is 2 minus x. If this was 1, wouldn't this be 1? Wouldn't that length be 1? If it was negative 1, wouldn't that width be 3? 2 minus negative 1, it would be 3. So it's 2 minus x everywhere in there. What's the height? How tall is this? What's the top? No, the top's not 11. It's not. The top is 11 minus x squared, correct? It's got to be for any value of x. So the top is 11 minus x squared. What's the bottom? X squared plus 3. Please let this make sense. If I give you any rectangle sitting anywhere, and this is 5 and this is 1, how tall is that rectangle? 4, right? So what was the top? This. What was the bottom? This. So how tall is it? Top minus bottom. So every step needs to be its own distinct step. There's no need to worry about any other. The minute you figure this out and this, great. Great, here. Now drawing a rectangle, great. Now look at the top and the bottom. Look at how far away it is from the axis. I mean, each step. Right? You don't have to worry about everything that's going to come later, what came before. Or guys, I think that always gets in your head. So what's the height going to be? It's going to be 11 minus 3, so it'll be 8 minus 2x squared. Yes?
How did you get the radius again?
Oh, drawing a rectangle could be anywhere in here, correct?
Yeah.
And so if I would have put it here, this would have been some x value. Yes?
Yeah.
So the radius always starts at the center and goes out to the thing, whatever the thing is. In this case, it's a rectangle.
Yeah.
And how long is this? Wouldn't that be 2 minus x?
Oh, okay.
Yeah. Do you see what I'm saying? So this is why you draw it. Put in the radius. I mean, give yourself visual cues, right? Otherwise, it's going to be really gross and disgusting. You're going to try to go, well, it's always this. No, it isn't. It depends on where things are. Now I can just throw shit in. So it's going to be 2 pi, and it's dx. So again, what's this going to be? Yeah, x is going from -2 to 2. R is 2 minus x, and h is 8 minus 2x squared. So it's just a little foiling, integrate, blah, blah, blah. You can do your little twice this, 0 to 2 if you want to. If you don't notice that, who cares? Yes?
Why is it not from 3 to 11?
Oh, because 3 to 11 is what which variable is doing.
Why?
And we're integrating with respect to. So I love your question. Nothing wrong with it at all. It's beautiful. The minute you determine this, you kind of write it for yourself and you keep going back. You keep going back. Go back, right? So, okay, what's the one? Oh shit, it's dx. What's the x doing? Right? That's why you write this down so you can always kind of go back to it. Does that make sense? And these are both functions of x, thank God, because that's dx, right? So there's a bunch of little checks and balances. They're supposed to help you, not be all this other shit you got to worry about. Write that down and it keeps you on track. And of course, what's this step? This is this should be the easy step, right? Foil, polynomial, who gives a shit, you can do it.
If you do have trouble doing this, come see me. Because we should not have any, this should be like, oh, thank God. If I gave you this problem, you have to say, oh, thank God. Or thank whatever. Like Spaghetti Monster, thank the God of Coffee, thank. It is his name. Okay, so real quick, let's get less specific for a moment. So if I had a region, let's see. Say I got this region here, right? Let's say this is at the y and this is g. I don't want to be this specific. Hold on, that's a little too specific. Sorry. Say I just got blah blah blah, blah blah blah. Who cares? It doesn't matter. So I got some region. So say I'm rotating around the x-axis. So what I really want to do here is not specific stuff. I just want to see why this makes sense. If I'm doing disks, I'm going to locate my disks. So if I rotate this region, it's going to be like this, right? I can do this. That's not bad, right? And again, you don't have to draw 3D. So if I'm doing disks, I step along my rotation axis, because this is the rotation axis is the center of my, I drew this way too far down, but that's all right. It should be right there. Screw it, it's all right, Jeff. It should be a circle, but it's like, whoa. Okay. So the radius is going to be from the x-axis out. So that's why it's integral dx, because I have to step, whenever I take another step in the x-axis, on the x-axis, I get another disk, and then I add it, and then I add it, step, add. That's why disks are integral d, whatever the axis of rotation is, right? They kick a lot of ass in that way. They have a lot of other problems, but stay with me so far. And again, this is what I spell out on this sheet. In the very first little paragraph, I try to explain why they each are dx or dy. If I was to do the same region, but I was to use shells instead, okay, I'm going to go around there. What would it have to be if I was using shells? Well, let's see. I would want my, this is a horrible, I'm going to change it. I'm just going to make it that just for the moment. Okay. I would want my rectangle to be like that, right? So I would locate, where else could I put a rectangle? I could have put it here for me. So do you see how they're moving along the y-axis? So with disks, I find my disk as I move along the axis of rotation, I find my disk. Shells, am I moving along this axis to find my rectangle? No, I'm moving along the other axis to find my rectangles. That's why this would be dy, because I'm moving along this axis to find my rectangles. I really want that by itself to kind of make sense why they are what they are. The more you understand that, the easier it is to set up what you're doing. Okay. And again, I'll basically say what I just said very quickly on that sheet. Okay. And of course, both of these methods, assuming I could get this, whatever these functions are, in the right format, they would come out to the same answer. Because they're the same rotation stuff. All right. So let's see. The let's maybe do one more, yeah. Let's do one more example of this. Do you want a shells or a discs? Or do you like, just do it, Jeff? Or do you want to be surprised? I don't know. Do one that you can do both ways? I think that this will do that. Let me see. I was looking at this guy. Maybe not. That would be gross. Okay. Do one you can do both ways. Oh shit. All right. Okay. Let me see. It's always tricky. It's tricky. No, it's always tricky. All right. Let's do this. Y equals x squared. Y equals 1/2 x. That makes sense, Jeff. I don't think. Let's do 1 more. Okay.
Would that just be negative x?
What do you mean?
Oh wait, this is 4. I thought this was negative 1.
No. Yeah. And I want this. So I want to find this region. So what I have to do first.
See where they intersect.
See where they intersect. I like it. So before I can grab it, I need to get some points. And the most important points are where they meet. Right? So if I do x squared equals 1/4 x. I can multiply by 4 if I want to. Bring the x over. Is that cool? I didn't have to multiply by 4, but I did. Okay. So x times 4x minus 1. So I get x is 0, x is 1/4, right? So what points are we talking about? Talking about point 0 something and 1/4 something. Ooh, Jeff, you made it really gross. Oh, I'll do that. It's kind of gross. I don't care. What are the points? What are the points? 0, 0. If you plug it 0, and either one of these is 0. Any other point? 1/16. Either one of these, you plug 1/4 in, you get 1/16. I love that. That's a quick little check. If they're supposed to meet at those points, they better be the same point, or else they don't meet. So what kind of scale? Everything's happening in the first quadrant. So let me make this better. There. So I'm going to make my scale something different, right? So I'm going to go 1/4 here and 1/16 there. It's crazy. Because I got control. I'm the human. Man. So it's 0, 0, and 1/4, 1/16. We'll do this in different colors. Let's see. So we'll do this one in red. Oh, dude, red. Hello. And we'll do this one in blue. So the blue one is easy. How do I draw the blue one?
Straight line.
Straight line. Wah! That's awesome. And the red one is going to be, is it going to be
It's gonna come under concave.
sunken or bloated? It's going to be sunken. Right, because the parabola goes like that. Okay. Is that the perfect curve? No, I don't give a shit. Right? All that matters is I know now where they are relative to each other. Right? So if I want to go, if I want to rotate this around, it doesn't matter. No, it doesn't matter. Around the y-axis. I like it. Now let's do discs first. Let's say it's forcing you to do discs. Right? I would have to be, what's the next thing I want to do? So I graph the region. It told me rotating around the y-axis. And it tells me I have to use discs. It's integral d what? d1. Beautiful. That's going to control your life for the rest of this problem. Right? That's why you write it down. Integral d1. So what's the immediate issue with the stuff I have? So functions of frickin' x with the shit. All right. So yeah, called it. What would this be now? Root y. I love it.
Now I know it's positive root 1 because it's positive. Yeah, that's why. Okay. And then what about this guy? 4, 1. I like it. And here's my axis of rotation. Put a dotted line in. So what do I need to figure out now?
The inner and outer.
Let's be a little more specific here. I need pi integral a to b r squared. Yeah. Well, that's fine. R outer squared minus r inner squared. dy. I know it's got to be these. How do I know it's got to be 2 radii? Not hugging. Oh. I had no idea the word hug would come up so much in calculus, right?
Will pi always be on the outside?
Yeah, it's a constant. I mean, it could be on the inside, but why would you do that to yourself? Okay.
We already know we don't have to do all like the y-axis and then it's just a 0.
No, it isn't. So we're talking about this region here,
Oh,
right? Right. It's the one bounded by those functions. That's why we found the points of intersections. Now we got that banana. That's strangely flat on one side banana. What do I do now?
Plug everything in.
Do I have stuff to plug in yet?
Under radius.
I didn't even get my radii, right? In fact, that's not, I didn't even get my radii. So how do I get my inner radius? Where do I start drawing from?
The y-axis.
Because that's the axis of rotation. Whatever the axis of rotation is, start there. I'm going to stop when I hit a wall. I love it. And the wall happens to be 4y. So my inner radius is 4y. And then, outer radius, past that wall and then stop at the outer wall. The outer radius. Rare one, it's crazy. All right. So that's kind of nice, because now it's dy, right? So what are my limits going to be? 0 to 116, because that's what y is doing. You guys, this is stupid important, because then you can just kind of keep looking back at it to keep yourself straight, correct? You want to be nice to yourself. Several ways you can be nice to yourself. Make a good scale so you can see what the shit's going on. Don't do this and then have, okay, here we go. Oh my God. No. Why be so evil to yourself? Write this down so you can reference it all the time. So the R outer, oh yeah, I'm sorry. So the limits will be 0 to 116. R outer was square root of y squared is y. That kicks so much ass. Oh, little, maybe poor little dude. So pretty cool that, right? Oh, you're dying too. Oh shit. And the R inner is 4y. Right? And now you just have to square that, integrate. Let's go ahead and do this one for once. So this squared would be 16y squared. Is that cool? What's the integral of y? Yeah, 1/2 y squared. What's the integral of 16y squared?
Negative 16 y cubed.
I like it. From 0 to 1/16. And now you just plug that in with calculator, right? It's going to be on the small side because, I mean, this is a pretty tiny little thing. Zoomed in on.
So if you move the rotation axis like 1 over to the left.
Yes, good. If the rotation axis would have been x equal -1, then both of these radii would have just been 1 bigger. It would have just been +1. Now that would have desperately sucked. Not too bad. But it would make these worse, you know, right? And they have to foil instead of just, right? Okay. Now, I almost don't care what that is, but if somebody figures it out, tell me what that number is. What if I was forced to use shells? What would I do? Dadgummit. Here we go.
This is dead from the beginning. So,
Oh, look at that.
ooh, sorry, easily used. 1/16, 1/4. So I'm going to sketch our graph again. That's roughly right there. That's fine. Okay. So we're still going around the y-axis, right? Yes. Now I'm being asked to use shells. So that's going to be integral d what? Good. Let's go ahead and fill this in with the general stuff. dx, because discs would be dy, so shells would be dx. So I always just start with what discs would be. Shells is the opposite.
Why did you do 2 pi?
Say again?
Why did you take out 2 pi instead of just pi?
Because the idea of shells is based on cylinders, and when you open this up, this is 2 pi r.
Mm.
So this is 2 pi r times r. I'm doing something wrong. Oh, times h. So 2 pi r h.
Got it.
Yeah, so it's 2 pi r h. Why did I erase? So the real quick thing is area pi r squared, derivative 2 pi r. That's the circumference, and that's what, when you open it up, that's how long that is. Okay. Fine. So you've got everything you need. Yeah, this is kind of beautiful. You know it's dx. Everything's got to be in terms of x. You know you need to figure out a, b, r, and h. So now you can focus on each of those, like 3 different problems. A and b are easy. Yes. What's a and b? 0 to 1/4, because I'm interested in the x direction. Yes. How am I gonna? Are my rectangles going to be standing up or laying down? Standing up, good, because they have to be parallel to the axis, so that when I have one, I can kind of do this to it and get a nice shell, a nice cylindrical shell. So they got to be standing up. So you can just draw it anywhere in there. And that's why I don't need inner outer radius, because I'm not including any empty space. I'm only including what's in there. So how do I locate that? Where is that? Do I locate it here? Yeah, so that's just some x value, right? And my axis is here. So what's my radius going to be? X. And again, if it would have been -1, it would have been x plus 1. X minus -1, x plus 1. So radius is x. What's the height? Okay, well, what's the top?
The height is x squared minus 1/4 x.
What's the top?
Oh, yeah, 1/4 x minus x squared.
And the top is 1/4 x. And the bottom is x squared. So then it's going to be 1/4 x minus x squared. I really pleased to see that, right? But so how tall is this rectangle? Well, what's this? What's this? And subtract. Big minus small, so you don't get some negative freaking rectangle and suck all of reality into it. And then you just throw shit in, right? So then this would be r is x, h is 1/4 x minus x squared. And see how this is actually better than the discs? Would you guys agree with me? Because you don't have to foil shit out. Well, this is not that bad. It's about the same. It really is. But now we should get the same answer. So let's see, 2 pi integral 1/4 x squared minus x cubed, which is 2 pi. This will be 1/12 x cubed. Is that cool? Minus 1/4 x to the 4th from 0 to 1/4. And supposedly, we should get the same number. What do you get?
Pi over 1536.
Pi over what?
1536.
Sure.
I checked.
I like it. It's fun. I don't know, so, I mean, what's important is, what are the steps? What motivates me to do the next step, right? Not what gets you out of bed, but what is it about the problem that tells me what to do next? And one of the most important steps, of course, is that. Because that controls everything after that. Okay. All right. Oh, man. Oh, good. Okay, I was looking at the wrong. Now, what's kind of nice, you would hope this would be true, that the last section in chapter 6 compared to this is really, really crazy nice. It's beautiful. It's bodacious. Right? So pretty got what they want from the blue and red banana top. Dooby-dooby-doo. Great. So, here's the idea of this. Let's start off with a nice, easy problem. Sure. All right. We don't even need intervals for what I'm about to ask you. What's the area in our triangle? That would be 1/2 the base of the height. So 1/2, 4 times 2, which would be easy, easy, easy. All right. So if I integrated, what was y equals 1/2 x from 0 to 4, I'm getting at 4. Because that's what it tells me, the area between the x-axis and that function, which just tells me the area, correct? No? So this, yeah. All right. Now, what do you believe is the average height of this triangle from 0 to 4? That's a weird question. Well, what's the lowest it is, the triangle? What's the lowest height as you go from 0 to 4? What's the lowest height? 0. What's the tallest it gets? No, come on. The tallest it gets.
Oh,
2. Right? Now this one's kind of easy because it's constantly moving. So the average height would be 1. Now watch what this relates to. If I were to smush this into a rectangle, isn't the easiest way to do that is to chop off this and put it there? So if I reorganize the area I'm working with into a rectangle, then the average value is how tall the rectangle is. Right? You know, stay with me. Let's see, how am I going to do this next time? Okay. So let's say I have some region, barf, and I get, here, make it like this. Right, so this is f of x. Let's say that I calculate the area for this, and I get some number, W, right? Not W, one second. I get area equals some number. Stay with me, this is interesting. I really want you. And how would I accomplish that? Wouldn't I just integrate? Right? Simple? Okay. Yes, is that? Now, if I were to smush this into a rectangle, how would you figure out how tall it is? How long is it? How long is it? B minus A. The length is B minus A. What's the area? That. So how would you figure out the height? Let me give you a concrete example. So if I tell you this area is 180, and I tell you that this is 20, how tall is it? 9. Area divided by the length, yes? So here, this would be the area divided by the length, right? So if I take the area divided by the length, I get the height of the rectangle it would look like if I smushed it into a rectangle, which is the average value of that function. So if I do smush this into, I could take this bit and smush it in there, right? So then I would get that height. That's the average value of the function. All the negatives, all the positives. Here's another way to think of this. How do you get the average of a set of numbers? How would you get the average? Add them all up.
Divide by how many numbers there are. Just
Number of numbers. Right? Right? All right, what does add them all up in calculus mean?
So,
Integral. Integral's job is to add it up, right? So add them all up would be the integral. And then how many are there would be this. It's another way to think about it. This I don't like as much because it's a little bit weird. I like the idea if I just take the area I'm given, well, I can calculate that area. I know how to calculate the area. And I divide it by the width, or the whatever you call it, the length. I figure out the height. And that height would be the average value the function takes on. So when they ask you to find the average value of f of x, let's do a problem. Wouldn't that be neat? All right. So let's say I have f of x equals x squared. And I want to know the average value from x equals 1 to 3. That's what that says. So basically all I do is find the area and divide it by the length. So it would be, what would be minus a times the integral a to b f of x dx. So what's this going to be? 1 over
3 minus 1.
2 integral 1 to 3 f of x. That's going to find the area. That's going to be, well, what if it was a rectangle? How tall would it be? And that's the average value that the function takes on. So what is the integral of x squared?
1/3 x cubed.
Yeah, x, okay. 1 to 3, so then I get 1/2 of 27/9 minus 1/2 of 1/3. So I would get whatever the hell that is. 13 thirds? Is that right? I don't know. Okay. So if I look at the graph, look at the graph of x squared from 1 to 3. If I were to smush this into a rectangle, it ends up being 13 divided by 3 is like 4 1/3. So here's let's see, that's 8, so 4 that'd be 5. So 4 1/3 would be about right here. So this is the average value it takes on. It's a little bit less than half because aren't these a lot lower? I don't know how to explain this. Kind of makes sense, does not, because most of the numbers are lower than a straight line would be. A straight line, which is the average, would be right in the middle. this kind of bows under that, so it's a little less than what that would be. Maybe. So basically took this, shoved it there, made a rectangle out of it. Freaky shit. So relatively, this is like section 5.3 with one extra step. You see that? That's section 5.3. Just integrate that. Yes? And then you divide by the difference of these. That's all this section is. Which is a little crazy to believe after all the shit we just went through. You know, like the next section, I don't even want to know, and it's a nice little fresh breath of fresh air, right? Oh yeah. I do have somewhere practice test. What is the test? Friday. Like number 6. Let me see. Did I ask you it there? No. Oh, no. Why did I ask you there? Oh, number 6, I would ask you, I could ask you something like the average value for f of x in the region. Does that make sense? That would be like from this. I don't know why I didn't put an average problem down here. Oh well. So one thing you could do is just kind of scan this and say, does this look familiar to me, right? Yeah, number 6 is a lot going on, right? See, D, E, and F are going to be rotations around different axes. Okay. So I'll have an answer key for that on Wednesday. We're not doing anything new before the test. Next week we'll do some out of chapter 8. I still have to tell you what the homework is. The homework is going to be very short. I don't like to slam you with a lot of stuff because some of you guys just started chapter 6, so you need to, don't want to put too much more on you. You got that stuff done. Okay. I think that's plenty. What do you guys think? Enough? Okay. Let me know if you have any questions. Otherwise, I'll see you Wednesday at least.